Okay, we're doing module 3 now. We're going to use percents to deal with percent changes. And we'll learn how to do that. Let me first mention that the result of adding or subtracting a percent, a percentage of an amount from an amount can be computed using multiplication by a single factor. Now that phrase, multiplication by a single factor, is something I'm going to use in the instructions to make sure that you are actually going to be applying what we're learning today. There's other ways to do it, the longer way that we learned in the last homework, but it's going to be important that we be able to condense our steps down using this technique, which we're going to go over right now. So I'm going to highlight that phrase and emphasize that's what we're going to learn to do today. There's going to be some formulas. A quantity increased by P% is equal to, I want to label what that quantity is for the purposes of the formula. A quantity X increased by P%. My bad. Okay, so whatever that quantity is, that's your X. I'm going to put it here on the right, and then we're going to put the factor in front of it. So there's going to be a single factor here, referred to in that phrase right there, that we're going to get by using 1 plus P over 100. That is that single factor. It'll require us to add to 1 some decimal form of a percent. Leave a little space here, because I'm going to write something on there. I'll write it now. What this is the 1 represents 100%. Side note, you don't have to write this down, but just to be clear, when you have 100% of something, and you want to convert to the decimal form of 100%, you move the decimal point 2 places to the left as usual, as we've always done, and you get 1.00. Or you can omit those zeros, since 1.00 is equivalent to 1. So when you have 1 full candy bar, that's the same thing as having 100% of your candy bar. It's not a portion of it, it's all of it. That's what this 1 represents here. The P over 100 is going to be the decimal form of the percentage. So you're adding to 100% P%, and that's what that factor is going to be. It is a percent in decimal form. A quantity X decreased by P% is equal to an expression that's very similar. We're going to have X there. We're going to multiply X by a single factor. And that factor is going to be 1 minus P over 100. It looks very similar, but this time we're subtracting a percentage. So it's 1 minus P over 100. Okay, again, I'll put over here. Same thing applies to that, but this is the decimal form of the percent. In fact, when I write it, I'm not going to bother putting P over 100. I'm going to go straight to the decimal form, as you'll see when we get to an example. Decimal form of a percent right there, P over 100. We've seen that before. This 1 represents 100% again. And then we're subtracting p% off of something. And that's how we're going to compute something decreased by p%. All right, I have those formulas, or a condensed version of them up here, so I can refer to it. I'm going to be using that. Not right away. We'll build up to it and relate it to the things we've done in the past. And by the past, I mean the last lecture, the last module. Suppose a meal costs $45. We'll keep it simple round numbers, not any weird down to the penny yet, just so we can follow along a little bit easier. And we want to leave a 12% tip. 15% is conventional, but I don't want to keep using 15, so I'm going to give you weird ones that may not necessarily be considered a good tip, but we'll go with 12% this time in this fictional scenario. Okay, we're not getting to the new things yet. I'm going to go with the old school way, which is to just compute the tip first. How much is a tip? And then what will be the total cost including the tip? Okay, let me do my calculator. All right. So it's a percent of something. You don't have to write this down in your homework when you do this, but let's clarify. The tip will be 12% of your bill. And what we're trying to do is compute 12% of $45. And the equation form of it is percent in decimal form times the whole. This is your whole, the whole bill, and your tip is going to be a part of that. So it's going to be 0.12. I'm not going to write the whole equation where I write part is equal to percent times the whole. I know I just want that percent of the whole to compute it for our tip. So it's going to be 0.12, the decimal form of 12%, times 45. That's it. That's how you would compute a tip in this situation. We get a weird number of 5.4, that's dollars. It's the same units as whatever 45 was, $45. 0.4 of a dollar is 4/10 of a dollar, not 4 cents, it's 4/10. And a dime is a tenth of a dollar, so that's 4 dimes. Now, normally to avoid confusion, I think I mentioned it last time, to avoid confusion you would add in the 0 just to make it appear down to the cent, so people are clear about what that 4 is. It's 4 dimes, not 4 pennies. Okay, and that's it. That's your tip. That's what we did last time. And then for the total, we would just add that tip to the bill. So here's your meal, costing $45. And even though it was written without the 0.00, because it was an exact dollar amount, you can put it in the 0.00, especially if you're going to add something that has cents. We'll add 540 as your tip. Oh. Sorry, let me erase that for now. Don't write it, don't worry, I'm going to put it in. And then your total. Okay, and you get your bill like that with blanks for your tip and your total, and then you would compute on your phone calculator, presumably 12% of your tip, 540, and then you got to go ahead and write it in on your own. That's 12% tip, and then you have to do the total on your own. Add it together, and you get your total of $50.40. Okay, then you sign your name on your receipt if you're paying by credit card or debit card, and that's how you handle that situation. Okay, following up, I'm going to cram it right over here. Am I going to? Oh, no, I need more space, so let me erase. It's the same instructions. You have this in your notes. I'll refer to it later. I'll confirm we get the same answer. But suppose we don't need to actually know the tip, we just need to know how much money we're paying. Say we're paying in cash. You don't pay out $45 and then pay out $5.40 separately and keep them separate. Not usually. I mean, depending what restaurant. Usually just leave a bunch of money on the table that includes the $45 and whatever tip you're going to leave. So, in reality, you just need to know how much money total you're going to leave. Calculate the total. Just following into the same problem, including the tip. And here's where the instructions are going to be very specific of using multiplication by a single factor. And when you see those instructions on your homework, you're going to be following along with the formula that we just introduced. This is the tip. Tip is going to be a percent that's added to the amount that we have to leave. So we're increasing our bill by 12% and leaving that as our total. Okay, let's do this slowly. You're going to have a factor here. We'll talk about that after. But then you're going to multiply that factor by x. X being the original amount, 45, your bill. And you want to increase that 45 by 12%. We're going to put a 1 there. Leave a little space on top here, because I'm going to write something on there. And then P over 100 is 12 over 100, and 12 100th is just the decimal form of that percentage. So I'm not going to bother writing 12 over 100. I'm going to know at this point that that's equal to the decimal form of 12%, or 0.12. So that's the P over 100. All right. And then leave a little space here because I'm going to write something on top of this, but let me go to the next line and start figuring out that factor. Now that's the two pieces, but you can just add them together and you get 1.12 when you do. Don't even need it to be that big. Multiply by the 45 still, and that's how you're going to increase it by 12%. Then I'm going to do that computation, and I'm going to write little notes here talking about what this is doing. 1.12 times 45. 50.4, that's dollars. So again, we talked about 0.4. You probably add a 0, so it reads as $50.40. That's your total right there. Okay, and what this is doing, like mentioned up here, the 1, if you do this distributed property, which we're not doing, if you did distributing, the 1 times 45 gets added to the 0.12 times 45. So the 1 times 45 is just 45. That represents the 100% of the bill, the meal that you have to pay for. This 0.12 is 12% extra that you're going to leave as your tip. So this computation, this factor right here is 100% plus 12%. And when you add them, you get 1.12, which is the decimal form of 112%. So this single factor computation is basically computing 112% of your bill. 100% for the meal and an additional 12% for your server. And that's it. 112% of 45 is what we're going to leave. And so if you're paying cash, you don't need to know what tip you're leaving. You don't need to know the exact amount of tip. You just need to know that you're going to leave 50, 40, and so on, and then throw 4 dimes on there, and then just walk away. You don't need to do the specifics of the math that we did in the previous round. You just want to know how much money to leave on the table. And that's the idea, single factor. All right, let's do a different example. With a discount this time, which means that we're going to do a percent decrease. Suppose a coat costs $65 and the customer qualifies for a 15% discount. again, this one time, and then I'm not going to come back to it after this. I'm going to do it the old way of calculating the discount, 15% of 65, then subtracting it from the $65 and getting the total. And then we'll do it a single factor method. So here, what is the discount? The dollar amount of the discount. I should phrase it differently. I want to say how much is the discount? Meaning the dollar amount. We know it's 15%, but I want to know what exact amount of money is being taken off my price. And the main thing I want to know is what is the total amount I'm going to pay. After the discount is applied. Okay, so what is the total after the discount is applied? And presumably you still have to pay sales tax on top of that result, but we're not going to mix two things in one yet. We will be, but for now let's just pretend there's no sales tax and just do this discount. All right, the discount is, this is just 15% of 65. Is what we get off. It's percent of something. There's no need for me to set up an actual equation with an equals and the part, but we're looking for the part, and the part is equal to percent times the whole. $9.75. Yep. And that's your discount, $9.75. That is 15% of 65. All right, that's your answer for how much is a discount. Next, we want to find the total after the discount is applied. So this one is going to be, what is this, a code? 65. I'll put the 00 because I'm going to line up my discount. Make sure you understand it's being subtracted, so it's going to be a negative 9.75. That's why we were doing things where it's negative and rounding with negatives, because it does come up when you're subtracting things off of totals. That's your discount. And then we just compute that. 65 minus 975. 55.25 is your total. Okay, and this is it with all the details about the original cost, the discount, and the total that you're going to be paying. But if you don't care about all that detail and you just want to know how much is going to be taken off your bank account when you purchase via a debit card, let's do a single factor. We should get the same answer as before. Let's learn how to apply the single factor method. Following up to the same problem, calculate the total using multiplication by a single factor. Okay, you can skip a few steps. You don't need to write everything that I write in my notes. Is more detail than you actually need, but I do want to see, I don't just want an answer. I definitely want to see the factor times the 65 and then your end result. Here I'm going to go through a much more detailed step-by-step process of pretending I don't really understand it yet, and I'm just going to follow this literally first. And I'm going to multiply by x, the cost of the code before the discount is applied. So some factor times 65 is what we're going to be doing. That factor is going to be what we get when we decrease the cost by 15%. So 1 minus P over 100, again, is the decimal form of the percentage. So 0.15 is what we're going to be subtracting from 1. Leave a little space here. I'm going to write the same things I did last time. Leave a little space here. And then right here, we're going to figure out what that factor actually is when we do 1 minus 0.15. If you can do it in your head, great. If not, go ahead and do it in your calculator. It's 0.85. 0.85 to be formal. and then I'll finish this up and do the computation. 55.25, the same answer as before. A little bit quicker. One step essentially. I could skip this step if I could do it in my head. If not, it's 1.5 steps, let's say. Okay, that's your total right there. What is this factor doing? As before, the 1 here represents 100%. The 0.15 is obviously 15%, and you are subtracting 100% minus 15%. So if they're taking off 15% off of your bill, you are still paying the remainder, which is 85%. And so this computation that we're doing is just figuring out what 85% is of 65, because that's the remaining after the discount that you have to pay. So you have to actually pay 55.25. And that's how that single factor works. Let us from now on get used to using that. So it'll be handy later on when we have to have multiple things going on, and each time we're going to apply multiple discounts and tax and other things. And so we want to be able to just use a single factor, possibly multiple of those factors. Okay, let's start applying this. I will probably put the phrase using multiplication by a single factor, but even if I don't later on, we still want to get in the habit when we don't need the intermediate step and we just want the total, it'll be definitely good for us to get used to doing the single factor. Suppose we purchase sneakers for $125. Apparently the good pair. And sales tax is 9.5%. Calculate the total cost. No need to calculate the tax separately. We just want the total cost. And I will specify using multiplication by a single factor. All right, we need the decimal form of 12, sorry, we need the decimal form of 9.5%. Let's talk about that. We did it before, but I'm going to review. You can have mixed numbers percents. I've mentioned before that interest rates are often have 1/4%, 1/4%, 3/4%, sometimes 0.5%. California sales tax is also 7 1/4%. I did look it up, so it does have 1/4%. No, I'm not going to get into that now. I'm trying to avoid fourths for now. I will introduce it at a later date, but I don't want to overwhelm you too much now. But definitely at this point, we're going to start dealing with 0.5%. Now, anytime it's a mixed number, you want to rewrite the mixed number as a decimal, not converting the percent to decimal yet. That's a separate thing. So imagine we're just doing 9.5, and I want a decimal form of 9.5. Not worrying about it being a percent. I'm going to pretend it's not a percent yet. Okay, if you don't know the decimal form of that fraction, 1/2 is 0.5. If you don't know that, that's fine. You can literally do 1 divided by 2 on your calculator. And you get 0.5. When you add the whole part 9 to it, it's just 9 plus the 0.5, you get 9.5. And that's what that is. Oops, I don't want to write it in red. I want to write it in blue. Okay, so 9.5 is equivalent to 9.5. That's how you're going to do it. Now, that's not the conversion we need to do of a percent to a decimal, because 9.5% is equal to 9.5%. It's still percent. We didn't move the decimal. We just converted a mixed number to a decimal form of that mixed number, and now we're going to convert the percent to a decimal. Now you're moving it 2 places. 1, 2. You need to add a 0, and it becomes 0.095. That's the decimal form of 9.5%. Sorry, of 9.5%. All right, and we're ready to actually do the computation. I'm going to do it over here. Single factor multiplied by your sneaker retail price of $125. You can put the 0.00 if you want, but it won't affect our computation, so I'm going to omit it here. And then I will write out and this is this, what are we doing? Sales tax. So again, it's important you remember if you're subtracting that percentage or adding it, increasing it by that percent. Sales tax is added onto it, obviously, so we are adding the decimal form of it. And you can skip that step and just know that when you add 1 plus this, you're going to get 1.095. And that's fine if you just want to skip to this step right here. I do want to see that factor though. Whenever you do showing your work, I want to see, I don't want just the answer, I would like to see the factor you're using times the original cost of the sneakers before sales tax, and then do it and then give me your answer. I just want to see that step and then your final answer would be good enough for me. 136.875. Now it doesn't specify where to round, but if it's money and you want extra detail down, you're gonna, insist on being paid down to the penny, as a sneaker store will. You're gonna round to the nearest cent always by default. So it's not gonna specify necessarily, but don't leave your money like this. It's not a thing that can be paid. You gotta round to the nearest cent always, unless it says round to the whole dollar. But definitely don't leave it with a half a cent is what that represents. I'm going to underline the 7. I'm going to round at the 7. The digit to the right tells me I'm going to round up. I'm going to add 1. It's going to become 8. 8. That 8's not affected. Neither is a 136. So it ends up rounding up to 136.88. And that's the total cost, including tax, in one step using a single factor based on our percent increase concept. Okay, let me do another one. Suppose we purchase an item. I guess I got tired of coming up with scenarios, actual things to purchase. So an item with a price tag of $96.50. Sales tax in this scenario is 7%. And we qualify for a discount, specifically for a senior discount of 18%. All right. Oh, and what is the total cost? I'm just going to write what is the total cost, but that's assumed to be, presumably, after the sales tax is applied and after the discount is applied as well. Two things we're applying, a discount and a sales tax. I didn't specify which one should be applied first. Let's just try one way for now, and then we will discuss on whether the other order will change the actual total. If it does, we want to go with whatever's beneficial to us, but I'm sure the store will want whatever's beneficial to them, but it doesn't even matter. Well, we'll see. But here, let's apply. It doesn't matter. I'm going to do the discount first. Then we'll apply the sales tax. Apply the discount. I'm going to do this a little bit faster and not necessarily show too many steps as I did before, but discount is 18%. So 1 minus 0.18 multiplied by the 96.50. We'll apply the discount only. We will still have to apply taxes after that. Okay, 1 minus 0.18 is 0.82, I believe. It's late for me, so 0.82. If you get 18% off, you are paying 82% of retail price. Okay, and let's compute that. Notice it's multiplication, 0.82 times. I'm going to come back to that fact in a bit. 79.13. That's after you apply the discount only. I'm going to circle it just as it's not the final answer, but it's an intermediate step, an important one. Let's apply sales tax to that now. So now it's 79.13 we're looking at. Oops. Oh, I always leave that out, but you can put it in parentheses as well. Just note what all these numbers mean. 79.13 is a cost after the discount is applied, but then we have to pay taxes on it. One, taxes is adding it to it, and sales tax is 7%. Make sure you don't use 0.7, it's 0.07. Again, single digit percentage will have a 0 and then the 7. Be real, if you're stuck with that or it's getting tricky for you, take the extra time to move the decimal point 2 places. I'm kind of skipping out on it at this point. I don't want to waste your time. 1.07 is a factor that will calculate 107% of 79.13. $84.67. Okay, now that's it. Well, that's it in the order we applied it. Discount and then sales tax. Now, I want to go through the same computation again and talk about what we did, not going through all the steps. I'll just put or. But I need a lot of space. 96.50 is the original amount. And what we did first was we applied the discount. And applying the discount meant we were multiplying by 0.82, 0.82. Okay, and then we got that result, which was 79.13, and then to that, we then applied sales tax, a sales tax factor of 1.07 to calculate the total, including sales tax. So then we multiplied this result by 1.07. But if I had chosen to just tack that 1.07 right up here, it's the same thing. So I could have held off on all my computations and just did one single computation involving two multiplications, two factors. 0.82 times 96.50 is 79.13. Then we multiply by that and we get a result. It's the same thing as if we just had done 1.07 times 0.82 times 96.50. And I get 84.67. I didn't show the rounding, but we would have to round the 6691 up. Okay, so we rounded up on that one. I'm not going to show the rounding every single time. I'm getting away from that now. Okay, so this is the main computation I want you to know. 107%, I don't even care about that, but I want to show you that you can apply both at the same time in one computation. It's all just multiplication of factors, this time two separate factors. And so I'm going to ask a question that I asked earlier, but now that we have more information, you should be able to answer it. Does the order matter? Does the order in which we apply and I'm just going to use a general form, percent increases and or percent decreases. Matter? Does the order matter? It's not that important that you understand that it doesn't matter. No. We can see that we will just be multiplying by factors and rearranging the order multiplication, putting a 1.072 there and then 0.82 out here. Does not actually affect it. So no, because it's all multiplication. And I'll put that in. And and the order of the multiplication does not matter. That only applies to percent increases and percent decreases. Why did I abbreviate one but not the other? I'm getting lazy. So if you're applying several percent increases and percent decreases in this way, the order that you apply them does not matter. That's for percent increases and percent decreases because it ends up being multiplication. Okay, and like I said, this is not super important that you know this. It's more of an interesting fact. But I'm going to give you another example and talk about why the order does matter, what situation it will. Not for this, not for percent increases or decreases being applied, but I'll have another example where it's going to be a fixed discount of $25 off on this next example. You'll see in a bit. Okay, suppose we purchase another item, a different item, with a price tag of $163. Where sales tax is 8%. And then we have a coupon for $25 off. Okay, and that's important. That is $25 off, not 25%. Now I'm going to tell you right now, it will matter the order we apply it in, so I'm going to specify. Assume the coupon is applied first. Assume the coupon is applied before sales tax. Is computed. Okay, how much would it? What will be the total cost? And does it matter what the order is? Does it matter which order? The discount and sales tax are applied. I mentioned that it does. I want to have it formally addressed in your notes. We're not getting too much into this. I just wanted you to see more of the curiosity and get a feel for certain things. And I wanted to make sure we can handle a situation where you have a coupon or some sort of discount where it's already a dollar amount, not 25%. So if you have, don't write this down, if you have 25% off, that's 1/4. You're getting 1/4 off the cost. And now if you're getting 25% off a candy bar, you're saving a couple of cents. If you're getting 25% off a new car, holy smokes, you're saving thousands of dollars probably. But if you have a $25 coupon and you're using it to buy a car, a new car, it's not even worth the paper that, I mean, it's not even worth it. It's going to take $25 off of the cost of a multi-thousand-dollar car. It's not going to make much of a dent in your monthly payments. Anyway, this is a $25 off, not a percent. Okay, and I'm going to, since we're not going to get into this too much, I'm going to go ahead and write one computation. I'm going to use a lot of mathematical grouping. So the idea is, it says apply the coupon first. So we would take 163 and we'd subtract $25 off of that. And that'll give us the amount after we take off $25, obviously. Then we would apply sales tax. And normally the factor that I use, I've been putting in front. I've been following this order. But keep in mind, when other people do it, and when you see it done in the future, they may not necessarily keep it in that order. So this factor here, you could just easily, oops, it's actually this one, move it to the right side of the amount. So I'm going to put it over here. So I'm going to kind of go left to right now. We're going to take the amount, subtract off the $25 off, because it says to apply that first. That result's going to be grouped, so we do that first. Then we multiply by 1.08. Skipping the step of writing it as 1 plus 0.08, going straight to the factor. I will label things just in case you are confused later on about what all this is. That minus 25 right there is your coupon. That's sales tax being applied. Not just the sales tax itself, that's sales tax added to the amount, doing the one factor thing. So let me write applied so you don't think it's just the tax. It's sales tax being applied to give you your total. Alright, that's what we're doing. I would do it in steps. You could do it in one computation, especially if you have this kind of calculator where you can do the grouping. The parentheses there are there. Right above the 8 and 9 key there are open and closed parentheses, but you can use, you could type this in exactly as it's written, get a single answer, which is fine, I don't mind it. But let me just do it in steps. 138 is after the 25 discount is applied, and then we multiply that by 1.08. And we get our total, 149.04. Okay, but because it's subtraction, or even if it's addition versus multiplication, the order does matter. Does the order matter? I said it does. Let's put a tentative yes if you trust me. But don't just trust me. Let's work it out. I won't make you, I can't say that. I might make you work out both ways just to confirm it for yourself. Here, we'll do it together. And let me set it up this way and talk about how I'm going to write on one thing. We're going to take 163. I'm going to do it the other way. This one was applying the coupon first, then the sales tax was applied. Here I'm going to apply the sales tax, which is multiplication by 1.08. So I'd multiply those and get the result of, including tax, but before the discount, and then I'm going to apply the discount after in the reverse order of this one. That would mean I'd take this result and then just subtract 25 off of it. That's a different computation now. And because it's mixing multiplication and addition and subtraction, it actually comes up to a different answer. Okay, 163 with sales tax applied is 176.04. And then if we apply the $25 off after that, we get 151.04. Okay, so definitely don't give them the coupon after they've rung it up, because if they take $25 off after they applied sales tax, it's worse for you. Okay, so yes, the order matters. Different answer. Let me write that in clearly. This is not something I'm going to emphasize, but I did want you to see little quirks about this sort of thing. And for the first time, I wanted to make sure we could handle a dollar amount being discounted rather than 8%. Different total. Okay, another example of how the single factor will be handy, especially later on, because this is going to relate to things we do later on. Let me pause though. Okay, we're going to do an example that is a new example, a new type of example that involves percent increases. We're going to do interest. The money in a bank account earned 3%, and there's different types of ways of computing interest. We're going to for now stick with the simple version, which is annually compounded, and your homework for this particular lecture will also, homework 3, will also involve this type, so you don't have to deviate from this. Later on we're going to get into interest and the different ways of computing it, and we'll have a whole module on interest. But for now, just follow along with this method of annual compounding. I'll explain it with this example. I'm going to put this in parentheses because we don't really want to get into the details of that yet, other than just understanding what it means in this context, which is just increasing the amount in your account by 3%. Compounded annually. annually compounded interest each year. Okay, so whenever you put money into your savings account, it earns interest, meaning the bank will pay you for keeping that money in there. And sometimes your checking account gets interest, but not always. But definitely your savings account should be earning interest. And so if the account has $500 at the start, calculate the balance. Balance means the money in your account. When you check your account balance, you're checking how much money is in there, and it'll change, it'll increase based on this interest being added to it. Calculate the balance at the end of each year. Comma, over the next 3 years. Okay, so we'll talk about how the interest is computed as we go, specifically for this annually compounded. At the start, I'm going to work my way that way. At the start you have $500 period, and nothing happens. You just plop that money into your account and it just sits there, and you leave it sit. We're going to be letting it sit there for 3 years, earning interest each year. Okay, and the first year we're going to talk about how the interest is computed. Basically, they're going to calculate let me label this as interest. We're going to compute the interest first, and then we'll add it to the balance. The interest, when it's compounded annually, and again, for this homework, the assignment you have that refers to this is going to be the same thing. Basically, they're going to compute 3%, the interest rate of the money you have in your account that you've been letting sit for a full year. And we're assuming we're not withdrawing anything, we're just going to plop it in there and let it sit. And at the end of the first year, they're going to compute 3% of this as interest. 3% of $500. Let's compute that. We're not going for the total, so we're not doing the 1 plus yet. We will, I will talk about it, how it relates. But here I want to look at the details, so I actually want to do the 3% of the 500. Now I'm going to go straight to multiplication. We should be good and proficient in it by this point. I have to set up a full equation, but whenever it's percent of something, you're just multiplying 0.03, not 0.3, times the 500. And that'll give us $15. That's the interest that you've earned on your $500. That's 3% of the 500. Okay. Let's look at our bank statement. Do I have enough room for this? Okay. If you've ever seen a bank statement, sometimes they have a previous balance at the start, which was $500 previous, before they actually added the interest. $15, and then your new balance is now $515. I'm going to circle it even though that's not our final answer. Well, that's one of our answers because we did want the amount. Ooh, that's ugly. We did want the amount at the end of each year, and this is the end of the first year, for each of the first 3 years, or over 3 years. Okay, so that's 1 of 3 years that we have to do. Okay, so that's how it works. Now, what happens is, the next year, you don't earn another $15 of interest. Oh, sorry. Getting sloppy. Because what happens is you're earning interest, 3% interest on the money you have in your account, and you now have $515. So not only do you earn interest on this $500 that you're keeping in there, you're earning interest on the extra $15 as well, so you're earning interest on your interest. That term of earning interest on interest is compounding, where that's coming from. And again, we'll talk about that in more detail in the future. But for now, let's move on to year 2. It's the same computation, other than the fact that you are now earning interest, 3% interest on $515. And if you're looking for shortcuts to doing all this lengthy thing that we're doing each time, there's absolutely shortcuts, but you're going to have to wait patiently for that. Here we're going to compute 3% of $515 this time. It's a higher whole amount that you're doing the percent on, so you should get the same percentage though, but a greater amount should be a greater amount. Not much, it's slightly more. This time it's 1514. Oh, sorry, let me write the computation. The same interest rate, 3% still. This time it's a different whole of 515. And we get 1545. Okay, let's look at our bank statement. Our previous balance, again, we are assuming we are not touching this money, was $515. The interest that we earned this year, this second year, $1545. If you're going to align things like in this way, like a bank statement, sometimes they want the place values aligned, so let me do that. We might even want to throw in a 00 at this point because we are starting to deal with some cents. And I'm not having you, I'm trying to mimic a bank statement, but I'm not having you adding things in column. We're definitely relying on the calculator to do our computations. I think last time I just did that in my head because that was easy, but can I do this in my head? Yeah. Okay. Anyway, computed 515 plus 15.45. It's going to give us 530.45. Notice our interest is a little bit more because the money that it's based on, our balance, is a little bit more than it was before. Okay, and then we go to year 3 and then we're done, but oh my god, this is such a tedious process. So let me put the next question on that. Ugh, too long. I agree, that was too long. Okay, so let's not do the third year and let's start talking about a shorter way to do this. Now, first of all, I wanted to show you how the interest works and talk about that. And again, we will discuss it more later. But I just needed the end balance at the end of each year. So I just needed that, and the end of the third year, and I'm done. So I didn't need to do this whole thing. So let's see if we can, from the beginning, think about a shorter way. Now notice when we added to the $15 to the amount that we had in the account, that's the same thing as just doing a percent increase and getting the total. So, and on the homework I'm going to have a table ready for you. So you can kind of remember, oh, we're not doing it that long way of computing interest and then adding it for a new balance every single year. We're going to go straight to the balance for each of the years. End of the first year, second year, and third year. However, whenever you want to start off with, it sometimes helps you to have year 0. Year 0 would be the starting point. Year 1 would be the end of the first year. That's when you have your interest, your first interest computed and added, and in the second year and third year. But we need a starting point, and the starting point would be considered year 0. Just like when you start a stopwatch to time something, it starts off at 0 and then it starts counting the seconds and the minutes. Alright, now we want to basically, to tack on the interest into the $500, we basically want to increase that amount by 3%. You're adding 3% to it. So the single factor techniques says we can just do multiply by 1.03. That's going to give us 103% of the 500. As long as we did everything correctly, it should match the ending balance of the first year that I just erased. It's computing 103%. All right, we get 515. What do we do with that 515? Well, we earn 3% interest on that, so our balance will be that increased by 3%. So we multiply by another 1.03. $530.45 takes us to the total without giving us the actual interest, but we don't care. I just wanted the balance at the end of the year. I don't need a breakdown of the interest and the total. I just want the total. And the last one, which we did not do, but now that we see the pattern and what we're actually doing, we can get that last one, the final year of the 3 years, by increasing it by another 3%. And here we end up with some decimals. I'm gonna have to round it. You don't have to write this down, but at this point we should definitely be able to round things pretty quickly. Like I said, you do these computations, you get some fractions of some pennies, and you can't have that dollar amount listed in your bank account. It's going to confuse everybody, and you definitely can't pay it out. So we round things to the nearest cent, giving your customer or us every single penny. In this case, we will have to round down to 36. So we leave a 6 alone, and it's just 546.36, rounded to the nearest penny. Okay, and that's the balance at the end of the 3 years, increasing it by 3% every year, but earning interest on interest. Okay, I'm not quite done, almost, with this example at least. But I wanted to also mention, or give you a preview of later on, if we just I wanted the balance at the end of each year, so I wanted to see that one and that one and that one. But a lot of times we don't care about seeing it as we go. If we're going to drop some money into an account and just wait 3 years, we want to just know how much we're going to have at the end. So let's say the balance at the end of the third year, let's say we're just going for that. I'll say balance after 3 years. Which is that. I know what it is, 546.36. But let's say I was building it up, or I wanted to be able to figure out how to compute it immediately, fairly immediately. Think about how we got there. I took $500. I don't want to put the dollar sign. This is going to be the computation, sorry. I'm going to reverse the order of things I multiply by. Usually I do the factor, then the amount, but it's interchangeable, so I'm going to put 500 there. I'm going to note that the first thing I did was multiply by 1.03. That's not the balance after 3 years, that's the balance after 1 year. That would right there would give me 515. Don't write this down because I'm going to erase it. That right there is a 515. End of the first year. Now to go from there to the second year, we multiplied by another 1.03. So I want to take that and multiply by another 1.03. I could go back to the original, not bother to multiply it out, and just note that to get to the second year, I would multiply by another factor. And that right there would get me the second year's balance. And then how do I get the third year? I would multiply again by another 1.03. So 3 of these apply. It's 3 separate years of 3% increases to your balance. And we can condense that down using exponents. It's the same factor 3 times. 500 is separate, but 1.03, 1.03, 1.03 is the same thing as 1.03 to the third power. And we can do that computation once we get familiar with how to do exponents on the calculator. We are going to go through it in more detail, but you're going to hit 500 on your calculator, hit multiplication. No need for the parentheses, although sometimes you'll need it, but not in this case. You're going to put 1.03, and then you're going to hit a button on your calculator that's what's called the caret button. If you have the TI-84 or 83 even, the caret button is right above the division symbol, right about there. It's a button that looks like an upward arrow. That's called a caret. And when you do that, for some calculators it's going to give you that symbol, which means raised to the power of. So 1.03 raised to the power of 3. And then you would just hit enter, and you should get that before the rounding. So 546.363, whatever it was. Okay. Sometimes, especially in the TI-84, which I get mentioned as a little more advanced in the 83, when you hit that button, when you hit the caret button, it knows you want to do an exponent, and it gives you a little box there with a blinking cursor for you to enter the exponent you want right there. And the exponent that I want to enter right there is 3. So then you enter 3, and then hit enter. I get 546.3635. Again, we're rounding near cent. That's at the 6. 3 is still going to tell you round down. And we end up with 546.36. And so we will learn, not this lesson, for this lesson, the homework problem that's like this, I want to see the balance at the end of each of these years, so I want you to do this factor and get used to doing that. Later on, we'll get used to doing this and interpreting it this way. 3% increases over 3 years, and then do the computation, and I'll go into more detail about the calculator at that stage, and rounding obviously we already know. But so that's, again, just a preview for what we're going to do later on. For now, we can just treat it as increasing by 3% each step of the way. Okay, next example. Percent change, going to be coming in a little bit. Okay, next is we're going to learn how to calculate the percent change. What we did previously was learn to calculate the amount after a percent change. Here we're going to have the amount before, the amount after, and then we'll figure out what the percent change is. Calculating percent change. And it'll be a percent increase or a percent decrease, but generically I'll use the phrase percent change. The percent change, informal definition that'll need to be explained with an example. C is the percent or percentage of the original amount. That's important, that it's a percentage of the original amount. That is added or subtracted. Added to or subtracted from. The original. Okay, and in this regard, the original amount is often referred to as the base amount. And I'll probably use that term a lot. Okay, there's going to be a formula for it which we can compute and pretty straightforward, but a lot of times with uglier numbers especially, it's hard to know what's going on with it. I want you to have an intuitive understanding of percent change. So we're going to learn to do it graphically, with intuition, and without doing any computations. So I need the whole board for this. Okay, and for these I'm going to keep it in nice round numbers. Now, recall that 1/5, when you convert it to a percent, you do 1 divided by 5 on your calculator and you get 0.2. You convert that to a percentage. Move decimal 2 places to the right, going the other way from a decimal to percent, and until it goes past the 2 and past the 0, and you get 20%. 1/5 is 20%. I want a visual image of this via a candy bar. We did this earlier. Let me see. Just a small one. And we're going to cut it into 5 pieces. 2, 3, 4, and 5. Okay. So that's 1/5, which means that's, oh, I'm going to put the 1/5 up here actually. 1/5, chopping the candy bar up into five equal pieces. That's 20% of the candy bar. That's another 20%, and so on. It's getting too cluttered. I made it too small. Anyway, 20% for the first piece, 20% for the second piece, 20%, 20%, 20%. 5 of those adds up to 100%. And what we're going to be looking at is situations where we have multiple slices of those. If we have 2 of those slices, it'd be 40%. If we have 3 slices, let me write that out. No, I'm going to erase it and put it back, but if we had 2 of those slices, 20 plus 20 would give us 40%, or double. If we had 3 slices, it's going to be 60%, and so on. Okay? But 1 slice is 20%. So the answers here will be nice multiples of 20%, because I'm going to set it up that way. All right, let's see. Here are my instructions without doing any computations. You will have a formula to work with later that you can do computations for. You could apply them here. But here, I don't want you to. And my instructions in the homework, I will have problems like this, and I will specify I would like you to do these without computations. Determine, not calculate, because we're not going to calculate. Determine the percent increase / decrease. I also mentioned, even though it may be obvious to all of us, I would like you to specify whether it's an increase or a decrease. So be sure to specify, or be sure to indicate. If it is an increase or decrease. Again, it'll be obvious. It's not difficult to tell which one it is, but I want to specify. I want to get you used to giving me all the information. All right, let's see what we got here. So what I'm going to do is I'm going to draw a set of axes. I'm going to have a bar graph basically. 1, 2, 3, 4, 5, 7. Okay, this is going to be value in thousands of dollars. The value of a whole maybe. So that says value in parentheses. It says dollars and thousands of dollars. Leaving space here for actual labels. I'm going to go by 30s. Right here it's going to be $30,000. These are equally spaced tick marks, so 30 and another 30 is 60. Then 90, 120, 150, 180, and 210. We're going to see the value of something either go up or down and determine the percent increase or decrease. Now I'm going to have a bar for the year 2020. This year. Or, sorry, that's not this year. Last year. And again, these are going to be designed to be very nice. And that's going to be the before picture, the original amount. And then we're going to see what happens the following year, in the far off year of 2021. And then we're going to see it. Don't write this down yet, but it's either going to be an increase or it's going to be a decrease. And we will determine the percent increase or decrease and get an intuitive feel for that. Noting that we're going to be using 20% because I'm designing these specifically so that the base amount, which I erased that term, but the base amount is the original amount. Here's your base amount right here. I'm going to even specify it. The base amount is $150,000. Now these numbers here are not going to be relevant for this particular type of problem since we're not doing computations. What is relevant is the fact that I've designed it and I've marked off my axis so that the original stack, the base amount, is a perfect 5 tick marks, meaning we can easily chop it up into fifths using the guides here. 30,000, 60, 90, 120, and then 150, and that's 5 pieces. What percent is in each piece? What percent of the total value is in each piece? 20%, another 20%, another 20%, another 20%, and another 20%. Because it's exactly 1/5 each. So it's designed to take advantage of that. That's why I put that on the board. No, I'm gonna label it later. Okay. All right, and now you're gonna see what happens in 2021, and I'll give you. All right. And this will be clear on your homework, but this is intended. I gotta put a little dot dot dot. It won't have this, but it'll be very obvious that this is intended to be right there, 180. Okay. And what's a percent increase or decrease? Okay, so it's a percent of this amount. You basically got to figure out how many of these chunks got added onto here. And in this case, it's just one extra chunk. That's the increase right there. That increase, so it's for sure an increase, obviously, but that increase is what percent, that little chunk there is what percent of the base amount. It is exactly one of these. It is 20% of it. And therefore, that's what it is, a 20% increase right there. That's your answer. The value of this increased by 20% from 2020 to 2021. These percentages are percentages of the base amount. Okay, so we're going to look at that difference. And if it was, real quick, if it was up to 210,000 like that, it would be 20 plus another 20. It'd be a 40% increase. So it's basically these 20% chunks. Don't write it down. I'm going to keep this here. I'm going to give you other problems to do. Similar example. So I got to erase this. I know it's going to be tedious to draw this every time. I'm going to give you 2 more of these. It's just a before and after, and I'm not going to mix those up. I'll pretend we're always doing 2020 and then the future of 2021. I'll change this up though. I'll change up what it is. This is the population in thousands. This time though, it's not going to be 30s. It's going to be 50s. 50, then 100, then 150. 200, 250, 300, and then 350. That's going to be my scale. We're going to look at the percent change in population of this city. And my original amount will be 250,000. And again, I'm not just making this arbitrary. I'm not picking an arbitrary number and making my bar that high. I'm specifically looking at this axis and then making my base amount 5 of those, so that you know that in between there, between tick marks, is exactly 20%. That'll change, but for now I want to just stick with this idea of it's 1/5. All my bars can be chopped easily into fifths, and each of those fifths is 20% of that base amount. So 50,000 population is 20% of that total population in the before year of 2020. But in the after year of 2021, it's going to be down to 150,000. And I want you to think about the percent decrease on that. I'm going to leave it up. You're not using these numbers yet. They're not relevant other than to note that how many of these there are. 1, 2, 3, 4, 5 for the base amount. So each chunk is 20%. And how many chunks does it go down? How many of those chunks does it go down? That's your percent decrease. Think about that while I start drawing another one. is going to be cost in millions of dollars. Again, those labels are not relevant for what we're doing. Neither are the actual numbers that I use here. So let me do a weird one. 15, 30, 45, 60, 75, 90, 105, 120, 135. See the details on that? I think you guys are good. 720 resolution, so zoom in if you can't see that. It's 15, then 30, 45, 60, 75, 90, 105, 120, 135. My base amount's going to be 5 of those. Again, I'm taking advantage of the 20% and making sure you just get an intuitive feel for this. It won't always be this nice. Okay. And then the cost of whatever this is in millions of dollars is going to go up. Okay, so the graph's going to look like that. It won't have these little blue dash lines that I'm making to emphasize it for lecture, but you can go ahead and draw them in if you want. The main thing to note is, again, I've given you a base amount that can easily be chopped up into 5 equal pieces of $15 million each. Each of those represents 20% of the base amount. And this one's going all the way up to 120, and you got to figure out from there to there how many chunks that is. That's your increase. You want to figure out the percent increase. Here your decrease, what's missing? I don't want to fill it in with a filled in thing because that's going to look like it's filled in, but it's not. It's gone. That's the chunk that's removed. Okay, think about these. We'll talk about it, but I want to see if you can piece together what it is. I'll kind of walk you through it. That's your decrease right there. It's a decrease of 100,000 population, but that's not important. It's important about how many of these chunks here. This is a 20% chunk. That loss, that missing piece, is how many of those chunks? That again is 20%. Okay, I'm going to go through it. Pause it and text me if you don't understand, or think about it. Anyway, it's 2 of those. Right there's a loss of 20%. There's another loss of 20%. Total, that's 40%. 2 chunks of 20% were taken away. Okay, 40% decrease. That's your answer. Okay, so that's the idea. All right. Oh, this is a little bit off. Sorry. Okay, so there's your base amount. Yeah, no, good. Okay. And then that base amount of $75 million right there, they added on extra to the cost. We know each of these chunks is 25%, and how many chunks were added on to get to this new cost in 2021. Each of the chunks is 20%. Think about it. I'm going to go over it right now. Okay, so it's 1, 2, and 3. 3 20% chunks. So this is an increase, obviously. And it's 3 20% chunks, that's a 60% increase. So that's how that works. Okay? And then now we're going to learn how to actually do some computations, because in the future it's not going to be nice round multiples of 20%, but that does give you an intuitive feel about what we're trying to get when we're computing percent increases or decreases. Let me pause here, but now we're going to do some formulas. Oops, before we get to that, I did 20% chunks, 1/5, my base amount being easily chopped up into 5 pieces based on the tick marks on the graph. Tick marks refer to those things that I draw. That's a tick mark, another one, another one, another one, and so on. And what I did was I made my base amount always have 5 of those, so you can easily see what 20% is represented by. Okay, on the homework though, and don't write this down because this is just, it's related to your homework, but on your homework I'm going to change it up. I'm going to put in your homework, I'm going to have you recall 1/4 is 25%, and then I'll draw a different candy bar with 4 pieces. and it's showing that it's 25% each. And then my base amount's not going to be chopped up into 5, it'll be 4. So I'll have an example like that. And I'll remind you of 1/4 is 25%, and that's relevant because your tick marks will chop it up into a nice 25%, another 25%, another 25%, and another 25%. So you'll be looking at chunks of 25% on the homework instead of 20%. Same idea though, see if you can tackle that, and if not, text me and we'll walk you through it. I can jump on Zoom if you need. But anyway, let us talk about the concept of absolute change and relative change. The absolute change in a quantity, like a population or value or cost, is the absolute value difference between the final and initial value. I'm going to put or original value. So real quick, don't write this down. I'm just going to briefly talk about those terms that are in there. I was referring to them previously as befores and afters. Same idea, but the more formal term is initial. So in the previous examples, the 2020 population or whatever was the initial amount. And then, because we're looking at 2 points in time, a before and after, and the after is the final amount, your final weight after you dieted for 3 weeks or whatever. Okay, initial or final. Some books will refer to the initial as the original. We also noted that it's referred to as the base amount. These are all interchangeable terms, but again, that's what you're using to as the base and computing percentages of that. So that is important. But here I've got a bunch of those. I've used initial and original as well. Just so you know these terms and recognize them. Not that important to put that in your notes unless you need to. But here's just a mathematical version of that. The absolute change referred to here, oops, let me underline that as a important definition, is the absolute value, and absolute values are indicated by double bars. Real quick review that you have to write. When you take the absolute value of a negative number like 3, that's the absolute value of negative 3, you just drop the negative. If you take the absolute value of a positive number like 5, you keep it. It basically just drops any positive or negative, it drops any negative signs and always makes your answer positive. But it keeps the actual number itself. It just drops the negative sign if there is one. Meaning you always get a positive result. So in this situation, absolute changes, they don't care about positive or negative. They will subtract in whatever order you want. Final minus initial is usually how they go. Oops. Final value is the term I'm using. Minus the original or initial value. And if you get a negative when you subtract it in that order, you just drop the negative because of the absolute value. We'll see this in a bit. Now the relative change takes that result it takes the absolute change and it divides it by the initial or base amount. And when we get that, it's going to be a decimal. Well, yeah, it's going to usually involve a decimal. Not always. But we're going to interpret it as a decimal. So as a note here, the relative change that you get from that computation right here is the decimal form, or we're going to interpret it as the decimal form of the percent change, which is what we're ultimately going for. So we'll compute this, and then we'll just convert it to a percentage to give us the percent change. Some books will have percent change here as that times 100%. You have to write that down. And then, so you literally, that's moving the decimal point 2 places to the right to make a decimal into a percent. Things we've done at this point, hopefully mentally, not by actually multiplying by 100. But I won't leave it as a separate definition. I'll just make a note of that. That's how we're going to get to the important percent change that we're going for. Okay, let's do some problems. And eventually I'll just want the percent change, but initially I'm going to have, not initially, to start off with, I'm going to be asking for both absolute change, relative change, percent change. We'll build up to it. But later on you just want to go straight to that and then convert it to a percent. Because I'll just be strictly asking you about percent changes, the important stuff. Okay, the value of a home increases from $150,000 to $180,000. Sorry, I'm being lazy. I'm putting thou. Yeah, write up the whole word. Thousand. Was it thousands? Yeah, thousands of dollars. This is actually the example that we did first, via the bar graph that we did intuitively, without doing any computations. Calculate the absolute change. And again, it's going to be an absolute value, so it's always positive. But to indicate whether it's an increase or decrease, we'll just tack on the word increase or decrease. Specify if an increase or decrease. So we'll just write that out in words rather than attaching a positive or negative sign to it. I'm abbreviating. Increase or decrease. Okay. I'm not going to have you do relative change itself. I'm going to go, my next step will be to get the percent change, which will involve that and converting to a percent. Specify if an increase or decrease. Okay. Using the formulas, which I don't have written down, but you have them in your notes. You want to subtract. It technically doesn't matter the order, but generally they'll do final minus initial is standard. That will give you a proper sign. It'll be positive if it's an increase, negative if it's a decrease. But we will disregard that negative sign because we're going to be taking the absolute value. So that's what we're doing. And it's important we know which one's the final and initial. So it starts from 150. Don't put it in the order. It's not 150 minus 180. 150 is your original. It starts off at 150. And from 150, it increases to 180. So 180 is your final. I should have drawn the picture. Sorry, I'm going to, somewhere here, I want you to draw the picture. One, two, three, four, five, six, seven. Okay, and it was by, I'm recreating that same picture from before. If you can see it in your previous notes and maybe even draw an arrow to it, because it's going to be, it'll help us to have that as a reference. But I want to just redraw it up here. Okay. Let me label this. This was 2020, but we're going to call it the initial or base amount. This was 2021. This is going to be the final value. And that's how we're tweaking that problem. Okay. That's going to be 30. $1,000. If there's a negative, it's not a negative, but if you did get a negative, you would be taking the absolute value of it and just dropping the negative. So either way, we're going to get 30,000. Was it an increase or decrease? From 150 to 180 is an increase. So let's specify that. And that's it. $30,000 increase in the value. Feel free to abbreviate increase or decrease. I want you to specify it, but I don't care that you write out full words and full sentences. I'm more than happy to have you abbreviate things to, speed things along because I know you're busy with other things. All right, let's do the percent change. First, we're going to do relative change, which we already did, but I'm going to reproduce it there again. The absolute change divided by the original, the initial. I'm going to write in your notes here for the first time. It's important to divide by the base amount or the initial value. That's crucial. That's one of the common mistakes is dividing by the wrong thing. Not dividing by 180. Okay, up top we get 30,000. Or just 30, because we're doing everything in thousands. I'm going to talk about what happens if you don't. Basically, we're saying that increase was 30,000. Okay, here we're actually looking at numbers. When we did it intuitively, we just looked at chunks. But now it matters that that chunk is 30,000. And we want to know what percent that 30,000 is of the initial base amount. So, and we're figuring out 30,000 is what percent of this. And it's easy to see from my nice round numbers that it's 1/5, so it's 20%. But when we want to do 30 is what percent of 150, we talked about it and we've done it, you divide the part divided by the whole, and the whole being that base amount. You're always doing percent of that base amount. You divide to get the percent, you will presumably get 0.2. Let me just do it just in case. Yeah, that's your relative change, but I didn't want relative change, I want the percent change. So you're just converting that 0.2 to a percent. 2 places, 1, and you gotta add a 0. It's not 2%, it is 20%. Was it an increase or decrease? Obviously it's an increase. And we knew that already because we did it intuitively. It was nice round numbers, but that's how that works. That's what this computation does. Finds that difference of 30,000. And then figures out that 30,000 increase is what percent of the base amount 150, and it's a 20%, because it's just 1/5 of that in this nice round number case. Okay, real quick, you don't have to write this down. I've been using 180, 150, 30, but these are technically, I didn't write it here, but these are thousands of dollars. That's not, 30 is not the same as 30,000, so if you were to use the full standard form of these, $180,000, don't write this down, I don't want you messing up your notes with it. Just make a note of it if you're curious about it. Minus 150,000. As long as you're consistent using the standard form, 150,000, you can't use 150 there, you have to stick with, if you're writing the full number out, you gotta do it for all of them, you'll still get 0.2. As long as you're consistent. So it doesn't matter whether you use a standard form or you just chop things off and treat it as thousands, numbers of thousands. So yeah, if you're worried about that, it doesn't matter because it's all relative to whatever you're doing. Okay, I'm going to pause here, but we'll do some other problems. Okay, next one. I'm not going to do all three of the graphs, but I'll do the second of the two so you can see a decrease. So just going to be, I should have had that earlier, but computationally we're going to do this second graph that we did intuitively. Suppose a population decreases from 250,000 to 150,000. Calculate the percent change. Okay, so not two parts, just the percent change, not an absolute change as well, but it requires us to do it anyway in the numerator of the computation. So we'll ultimately be doing it anyway. Real quick, the graph. I'm going to put it up here again. You have it in your notes. I don't know if you want to reproduce it. And again, I'm going to label it a little bit different. This is our initial or base amount. This is our final instead of 2020 and 2021, but same idea. And I had it in 50s, right? 1, 2, 3, 4, 5, 6, 50, 100, 150, 200, 250, 300. I don't know if that's exactly what it looked like, but and it was 250, right? So again, this particular problem was designed to do intuitively off the graph by being a very nice 5-chunk candy bar. And then we're going down to 150. Okay, but we're not going to do it that way. We're going to do it computationally. So we'll go straight to relative change. And then afterwards, we will convert that decimal to a percent. Absolute value up top, divide by. Okay, final minus initial. Final is 150. Okay, so it starts off there. That's your base amount. It's from 250. Everything's going to be in percents of 250. But we want to do the final value minus initial. And then we'll divide by the initial value, which is again 250. And we'll label that there. That's your base amount. Let's go with base. And there's your initial. That's also your base. Which again, you're doing percents of that in this nice 20% chunks the way it was designed. Okay, let's compute this. 150 minus 250. That's, you do it on your calculator and you get negative. Negative 100. Now again, we do not keep that negative. It does indicate it's a decrease when you get a negative from final minus initial. But we're going to take the absolute value. And then we'll divide it by 250. Okay, so once you do that computation, you get a negative, you write that negative, and then you bring the absolute value down, and now you have to apply the absolute value. If you wanted to do those two in one step and just go straight to positive 100, that's fine, as long as you know that there's two different things you're doing. Subtracting and getting a negative, then applying the absolute value that's on the outside, bring it down here, and then apply it, and you get 100. That's how that works. And then for the last step, you figured out that this was a decline of 100,000 people. And then you wanted to figure out 100 is what percent of your base, which is 250. So if you did it the old school style, you'd be doing 100 is what percent, you don't have to write this down, of 250. The setup is your part is 100, that's the part that's missing, equals some unknown percent times your whole. Your whole is, this is your whole candy bar, your base amount. And then you end up, oh wait, that's right, yeah. And then you end up dividing by 250. And so to calculate a percent, you just divide part by whole and make a fraction and convert that fraction to percent. Again, that's a review of things we did previously. Calculator, 100 divided by 250. And it gives me 0.4. no need to write that. I was just reviewing how we interpreted it before, but now we're getting a little bit quicker on things. Now you convert that decimal to a percent. Remember that equation that I just erased gives you the decimal form of it. Move the decimal 2 places. That's not 4%, that is 40%. And it did specify, well, I didn't specify, but as usual, I want you to specify if it's an increase or decrease. Clearly an increase, sorry, clearly a decrease, and feel free to abbreviate the word decrease. Okay, so it went down by 100, that was your absolute change. We didn't ask for it specifically, but it was 100,000 decrease in population, and that turned out to be 40% of the base amount of the original population. Okay, we're going to do a couple more of these. Now it's not going to be so nice, it's not going to be those 20% chunks. We'll do some real life data where it's not always pretty nice. We might have to round those percentages to the nearest tenth of a percent. We will, I promise you. Design these to have some rounding challenges involved. And I think I've used real life data. The gross domestic product is a very common measure of how our economy is doing. It's in theory, the sum of all, the value of all the goods and services of the entire country. This is abbreviated GDP. When GDP is up or increases a lot, things are good economically, or at least we believe it. When the GDP decreases or doesn't increase as much as we hoped, things are not good. GDP, took a hit last year because of the pandemic, but it's coming back. Well, we're not going to even worry about that. We're going back to 2010. And back then, the sum of all the goods and services totaled to $14.99 trillion in 2010. And then sometimes they like to look at 10-year periods. To 2094 in 2020. Now it matters what specific point of the year it was measured in, because if it was in the beginning of 2020, maybe that's pi, and maybe if it was late 2020, then it would have gone down probably. I'm not worried about that now, but it would be worried if we were doing economic analysis. Here we're just getting used to that, so let's jump right into it. Oh, I'm not done with my question. Calculate a percent increase. It's not going to be nice, so round to the nearest. As usual, when we're doing rounding of percent, I'm going to make you do to the tenth of a percent and get used to that. I did it once last time, we'll talk about it again. Alright, but let's go to this. We're just doing percent change. We'll do relative change and convert it to a percent. Initial, $14.99 is your base amount. And then it changed to 20.94, trillion dollars, which I forgot to write. I'm going to abbreviate trill. In 2020, that was obvious but semi-important that I write it in. Okay. Final minus initial. Final value during that period is $20.94 trillion. It started off at this is now a 10-year period, but it's still final minus initial, and your initial amount in the beginning of this period was 14.99. We'll take the absolute value. That's going to be our absolute change. We can see it's an increase, but then to get the relative change, we'll divide that by the base amount. Again, make sure you know which one it is. This is not initial and final. It's the way I've written it is final minus initial. Go back to your problem. Which one is the beginning point? I labeled there with base. Make sure you are not dividing by 2094. You are referring to things as percent of the base amount of 14.99, where it started at. Okay. 20.94 minus 14.99. 5.95. So it was an increase of $5.95 trillion. Again, you don't need to put you don't need to put standard notation for all of them, as long as you're doing the same consistent trillions for all of these. 5.95 divided by 14.99. Okay, and I got 0.396931, a bunch of other digits that I don't care about, but I do want to keep quite a number of them because I want to recover rounding to the nearest tenth of a percent. So we're going to convert it to a percent. 2 places. Decimal moves there, so it's going to be 39 point something percent. The tenth place for the percent is going to be right there. So it's going to look, my answer will look like that. 39 point something percent when I round to the tenth place of the percent. Now, that's not a 6, or at least I don't know it's a 6 until I make a decision by looking at the digit to the right of the 6. So I'm going to be rounding there because that's the tenth place. I got to look at the digit to the right to tell me I'm going to round up. So it's going to round up to 7. Okay? If I work this out in more detail, which I did last time, I'll do it one more time, but in the future I'm going to kind of just breeze through this pretty quickly. 0.396931 ... is equivalent to 39.6931 ... percent. That's a percent form with way more decimals than I need. Then I'll note that they want the tenth place to be kept, to round there. So 39.6931% rounded to the tenth rounds up to 39.7%. Always specify it's an increase or decrease, even if you think it may be obvious. It even says it in the problem. They acknowledged it was... What happened? God damn it. I told you. Get used to this. I talk and I forget things. Okay. So in the problem itself, it's once I fix it, the problem itself acknowledges it's an increase. It seems like it's obvious. Why do I need to actually remind them it's an increase? We all know it's an increase. Well, just do it for me. As a personal favor to practice being thorough. Okay, real quick, one more, and then we're done. Got that down? Pause it if not, some erasing. Between 1990 and 2015, the global rate of extreme poverty fell from 36.2%. That means 36.2% of the world fell under extreme poverty back then in 1990. To 10.1%. So in 2015, only 10.1% were living in extreme poverty. So it's a good thing. I mean, it's not good that there's still 10.1%. We would like to correct that one day, but it's definitely better than much better than 36.2. Calculate the percent decrease. In the poverty rate. Round to the nearest tenth of a percent. Okay, I wanted one last example for you to do these computations, one that involves rounding, one that's actually a percent decrease. I would like you to work on this. Pause here. And another thing I wanted to address is the fact that sometimes the things you're seeing increase or decrease are actually percentages. And you can find when the percent changes, you can actually figure out the percent change in that percentage. So you can do percent changes of things measured in percent. You got to kind of keep track of what percent we're talking about. These are percents of people living in extreme poverty, and the percent that we're going to get at the end is a percent decrease in that percent of people living in poverty. It'll be the percent decrease of the poverty, what's called the poverty rate. Okay, but anyway, pause it here, see if you can do it. There is a question of should you just use 36.2? Well, 10.1 is a final. You don't need to put the percent symbol, but you can work with those. But the question is, I mean, I've emphasized 10.1 is not the same thing as 10.1%. These are all percent, so it's fine. If you wanted to use a decimal form, that would work as well. It might seem a little bit weird, but it will work as long as you're consistent. These will yield the same answer. Using decimal forms with all their percents will work and get you the same answer as if you work with whole number percents. These are technically percents. I just didn't want to clutter up my picture with all of those, but as long as they're all percents, you can subtract and then divide by that, and it's fine. And you don't, it's to the point you don't even need to put it. Notice in the last problem, I didn't write trillions. It was something trillions, trillions, trillions. They were all trillions, and I kind of just omitted it and focused it on those numbers. But either of these, I'm going to erase real quick. Make sure you know which one you're dividing by, even though I already wrote it. Think it through. Pause here. I'm going to go over it right now, but I want you to pause. Work it on your own. Do that rounding on your own. Make sure you're dividing by the base amount, which is the original, the 1990 poverty rate, when it was a lot worse than it is in 2015. That's your base amount, the initial. All right, I'm going to go, but I wanted you to do it on your own. So whenever I ask you, please pause it and work it out first. It really helps if you get your, work it out. Even if you can't figure it out, it helps you to work with it first and struggle with it and get all the pieces in your mind. And maybe you don't know how the pieces fit, but as long as you have them in your mind, once you see me work it out and iron out the wrinkles in your thought process, it will all click a lot better. Do not forget, this is important what you're dividing by. It's the base amount, the initial amount in 1990, which was 36.2. $10.1 minus 36.2 will give me a negative. What am I doing with that negative? Why, I'm ignoring it and dropping it, of course, because it's the absolute value, and I'm just going to skip that step and just go straight to 26.1. It was a decrease of 26.1% in the global poverty rate. What percent is that of the original amount, 36.2? Well, I'll figure that out next by dividing. Okay, I got 0.720994, a bunch of other digits. Make sure you're rounding properly. Converting to a percent and rounding to the tenths. I'm going to do it quicker than last time. Two places gives me 72 point something. But I want that digit rounded properly based on the digit to the right of that digit. So that's going to be where the 0 is, except I'm not going to keep it as a 0. Because of that 9 right there, I'm going to round up. So I'm going to bump that up by 1, and I'm going to end up with 72.1%. Was it an increase or decrease in global poverty rate? Thankfully, it was a decrease. Things are getting better despite what you may have heard. We're still not there yet, but yeah, things are getting better in the world, and so there was a 72.1% decrease in the poverty rate, meaning in the percent of people living in extreme poverty, which is a pretty steep increase. Sorry, pretty steep decrease. I was actually impressed when I found this. Again, still, we would like to rectify that. Anyway, that's it for this lesson. If you have any questions about this, again, just pause it immediately as soon as you have questions and text me, and we can go through it more slowly. And yeah, okay.